This is AQA Statistics, Continuous Random Variables 5. This video is about calculating exponential probabilities and deriving the exponential cumulative distribution function. Here we have the exponential distribution used to model a continuous random variable t with parameter 2. On the right hand side here we have the graph of the PDF, and the variable in question here is t, and then the PDF itself is going to be 2e to the minus 2t. Now what we should note then is that the intercept with the vertical axis there is 2. Here's our notation. T is distributed according to exponential distribution with parameter 2. The point here is to find a probability, and we're looking for the probability the random variable lies between 0.5 and 1.5. So actually what we're looking for is the area under the graph between 0.5 and 1.5, and we would usually find this by integration. Please pause the video and write down the integration you need to find the probability. Here's the integration. Now pause again to complete the integration. Here's the first step of the integration. Now substituting into three significant figures, we result with results in this probability here, 0.3180. What you might like to do is to enter the integration here, this one, into your calculator to confirm that you do get 0.3180. Please pause the video to read the question, write down the model and the probability that you require. So here the time in years is distributed according to exponential distribution with lambda equal to 0.4, and we're looking for the component still to be working after 3 years, so we're looking for the probability that t is greater than 3. Please pause the video to write down the integration that you need. Here's the integration. Make sure that you take note of these limits here for the integration. So we're looking for any value of t that is greater than or equal to 3. Substituting in, the probability turns out to be 0.3012. So that's the probability the component will still be working after 3 years. Here is the cumulative distribution function, or CDF, for the exponential probability distribution. It comes in two parts. Here we can see that when t is less than 0, then the CDF itself is 0, and when t is greater than or equal to 0, it takes this form here. Looking at either component here of the CDF, we can see that f of 0 is going to be 0. So we can just write down f of 0 equals 0. And we can see that as t becomes large, as t gets much bigger, so as t, say, tends to an infinitely large value, then f of t is going to tend to 1. The reason for that being that this second part here, this second component of the CDF, will tend to 0 as t gets large. Now we can think of this graph as a lookup, so that we can look up for any value of t. Then we can pick out the value here of f of t. And we can find f of t by integration, and we'll be having a look at doing this on the next slide. Here we see the PDF for the exponential distribution, and we can do a definite integral from the lowest non-zero value of the PDF up to t of that PDF to get the cumulative distribution function. Please pause the video to derive this function. The integration is similar to those we've done before, but here we see lambda instead of the numeric values of the previous two examples. If we substitute in t, then we do, having cancelled lambda here, then we will get e to the minus lambda t, but e to the 0 we know is 1, so in this second bracket here we'll get minus 1, and upon simplification we get the required function for this CDF, 1 minus e to the minus lambda t. Please pause the video to read the example and to work out how to use the cumulative distribution function to answer the question. Firstly, here's a reminder that the probability that the random variable takes a value less than any given value that we choose is given by the CDF. And the CDF is this function here, 1 minus e to the minus lambda t. So we're going to need to substitute in the relevant values for lambda here and also for t. Okay, so lambda then is up here. It is 0.5, and although it's given as a Poisson distribution, we know that the other side of that is the exponential distribution, and then we're looking for a time of 45 seconds, which is going to be the same as 0.75 of a minute. We just have to be careful with our units in this case. So the probability we're looking for is going to be 1 minus e to the minus 0.5 times by 0.75. Now if we substitute those values in, then what we finish up with is 1 minus 0.6873 and finally 0.3127. So that's our probability that the time interval between arrivals will be less than 45 seconds. Please pause to read the example. In this case, we need to note that we're looking at the more than case. So we can adapt our CDF to look at the more than case by doing 1 minus the CDF. So we finish up with this slightly simpler formula here. So we can see then that the probability that t is greater than 5 is going to be e to the minus 0.5, which is our value for lambda, times by 5. And if we substitute that in, then we work out the value of 0.0821. And that's the probability the time interval between consecutive arrivals is going to be more than 5 minutes. Well, that's the end of this video, and the next video will be on the median of the exponential distribution.